The best spacecraft images of 3I Atlas. Maybe Titan doesn't have a liquid ocean. Planetesimals crashing in a nearby star system. And the first Superkilonova. All this and more in this week's Space Bites. In November, Comet 3I Atlas passed behind the sun from our perspective, and so we weren't able to get the best possible view. Now, we got some images from spacecraft that were orbiting around Mars when it made its closest approach, but I think, the general opinion is that people were a little bit disappointed by those images. Well, good news, on November 2nd, the European Space Agency's JUICE mission, which is on its way to Jupiter's icy moons, took a picture of Comet 3I Atlas. And this is the best one that we've seen from all of the spacecraft. It took the image from 66 million kilometers away, which is actually a little farther than the images from Mars, but it was in a much better position. The comet had gotten closer to the sun. It was more active. And so in this picture, you can clearly see the central coma from the comet. And then you can actually see two tails, and they had to sort of mark where those tails are. One is the dust tail, and the other is the plasma tail. And this is a very common thing that you see with comets, that they're essentially two different kinds of particles that are pushed away from comets by the solar wind. They move at slightly different angles because of the speed of the material coming off of the sun as it interacts with the comet. And we actually had to wait a little while to get these images from the JUICE mission because JUICE isn't able to use its main antenna to communicate with the Earth. The problem is that JUICE has to get relatively close to the sun, and so they use this main antenna as a thermal shield at the times when it's closer. And so they're not able to reconfigure the main antenna to use it to send back all the data home that it took when it saw these images of 3I Atlas. So we have to wait probably until February for all the data to come in on its secondary antenna system, but it will get here. And then there's a whole bunch of other instruments on board that were able to gather data about the comet. And of course, what's great is that this allows the spacecraft to test out its instruments on an object, on something that nobody was planning for. And then they can sort of look through any bugs and issues in preparation for when it actually arrives at the Jupiter system. We've got more information about this story from Matt Williams on the Universe Today site. Now, I've mentioned many times that Titan is one of my favorite worlds in the solar system, if not my favorite. Like, if I had one place where I think we should be sending more spacecraft, more submarines, airplanes, all kinds of stuff, that would be Titan. And the reason is that Titan, we know, has hydrocarbons on the surface of this world. It has lakes and seas made of liquid methane. It rains liquid methane, rivers of it. You've got hydrocarbons on the surface. And then you've got ice on the surface that kind of acts like rock on Earth. You have mountains made of ice. It's very bizarre. Sand made of ice that blows around in the wind, pelted by methane rain. It's such a bizarre world. But like a lot of the other large worlds in the solar system, it's thought that this should also have a subsurface liquid ocean. It has tidal flexing with Saturn that would heat up its interior, and that would cause it to have a liquid ocean underneath this thick shell of ice. And then that kind of brings everything together. You've got liquid water down below, but then you've also got hydrocarbons, the kind of raw materials that is used for life. And if there's some mechanism that goes from the surface of the world down into those oceans, then maybe this is how we could get life on Titan. Well, a new paper just came out that said Titan might not have an ocean at all. And so, yes, it still does have tidal flexing, but according to their simulation, they found that it's more like a mush. So a sort of ice water mush that isn't fully liquid in the way that you would expect an ocean, like maybe what's over on Europa or maybe on Enceladus. And what's important is that the sort of gravitational readings that you would get if you measured this more mushball world is very similar to the kinds of readings that they got from the Cassini spacecraft. And so this could mean that Titan doesn't have a liquid ocean underneath. And it could mean that maybe some of the other worlds we thought have liquid oceans, and maybe this mushy interior, it still has some tidal flexing, but not enough to actually turn it into an ocean of liquid, is something that will be more common common across the solar system. And so, are we going to go back to this time where like maybe there aren't a lot of ocean worlds out there? Anyway, stay tuned for this. I've got a story about this from Scott Johnson on Universe Today. The solar system looks calm today, but it wasn't always the case. And we see the evidence of just the mayhem that went on in the solar system early on in its history. There's a few great examples. One, of course, is the presence of the moon, right? The moon is thought to be caused by the collision of Earth with some kind of Mars-sized object known as Theia. And then you got the moon as the debris that collected together. But even when you look at the surface of the moon, like after the moon formed, it is pelted with large asteroid impacts that happened early on in the solar system, time known as the late heavy bombardment. And so now we are billions of years after that period, and the solar system is relatively calm, but we can look out and see other star systems that are earlier on in their history. And the perfect example of this is a place called Fomalhaut. And it actually contains 3 stars in this system. One's a red dwarf, one is kind of sun-like, another is actually a little larger than the sun. It's called Fomalhaut A. And back in 2005, astronomers were looking at it with the Hubble Space Telescope, and they detected this giant disk of dust surrounding this main star, and then worked out that this is the result of comets and asteroids kind of grinding together to produce this disk of material around the star system. But then just a few years ago, they used Hubble again, and they detected what looks like the presence of some kind of cloud in this disk. And they suggested that maybe this was caused by a collision. And now, just a couple of years later, they found another. And now, according to their calculations, this seems to be the result of planetesimals crashing together. So not full-size planets, things that are maybe in the hundreds of kilometers to thousands of kilometers across that recently crashed together. And I think what's important is that just a couple of years ago, one of those objects wasn't there. It's there now. So it's fresh. And so it might be that we're actually seeing a lot of collisions between planetesimals in this system. If we happen to see 2 of them while we're observing the system, for a star system that is about 400 million years old, similar to the late heavy bombardment in the solar system, it's thought that you would get planetesimal collisions maybe once every 100,000 years, and not a few in 20 years. And so this might dramatically change our understanding of just how much mayhem there was in the early solar system. It was not, there's a bunch of big planets, things calmly collided a few times, you got the moon, and then everything was done. No, maybe it was just nonstop, things crashing together until finally things cleared out to become the solar system that we see today. Got a story about this from Evan Goff on Universe Today. And then James Webb has observed another planetary system where it looks like there are comets that are actively falling into the inner system and colliding with each other. So this star system is called HD 131488. It's about 500 light years away, and it's only 15 million years old. So it's very young, and it's classified as an A-type star. So that's something that is hotter and more massive than the sun. And the observations from Webb show that there is carbon monoxide in the inner disk of this system. And this is not a very common observation. It's happened a few times before, but to see this carbon monoxide in the inner disk is something that's rare, especially with a star that's this hot. It has a lot of radiation. It should be blasting this material out. So astronomers wonder, where did this carbon monoxide in the inner disk come from? And they have sort of 2 rationales. One is that it's just left over from the formation of the star system. And so just the star hasn't cleared out all of the carbon monoxide that was present. It's working its way through it. The other idea is that there are comets that are falling down inside. They're crashing together, crashing into planetesimals, and they're continuously replenishing the carbon dioxide in this inner system. And where this matters for planet formation is that carbon and oxygen are 2 very common materials that we find here on planet Earth. And then the thing that's lacking is hydrogen. And so that will get you drier terrestrial planets like the Earth, Venus, Mars, Mercury, and less of the sort of gas planets and things with a lot of water and other volatiles in it. And so this might be the process that demonstrates that material was falling in, delivering and concentrating these drier elements while you weren't getting the hydrogen. Then maybe the hydrogen came later with other kinds of comets. Interesting observation, James Webb, but what can't it do? Got more on this from Andy Thomaswick. There are a few kinds of supernovae, but the main kind that astronomers see is when you have a massive star that has used up all of the fuel in its core, and then it implodes. And you get this bright explosion and this sort of expanding cloud of hydrogen, helium, and other elements that were present in the star as it was collapsing. A kilonova is when you have two neutron stars, which are sort of the results of previous supernova, that collide with each other. And of course, the famous example of this is the kilonova that was detected in 2017. Well, in 2025, astronomers detected another signal that said, oh, that's another kilonova. They used the same gravitational wave detector, LIGO. And then they made follow-on observations of this object using various telescopes. And they saw this expanding cloud of heavy elements, exactly what they saw with the kilonova event back in 2017. So case closed, kilonova, no problem, right? Well, astronomers continued to watch, and they saw this follow-on expanding cloud of the hydrogen, which is the kind of signature that you get from a supernova. And so they detected it through the gravitational waves that told them it was a kilonova, but then they saw this expanding wreckage that was kilonova, then supernova. And so the astronomers think that it actually was some kind of combined object, that you had a massive star and it was spinning rapidly, and then it went through this implosion process where it started to compact down inside of itself. And instead of just producing one neutron star, it was spinning so rapidly that the sort of core, as it was accreting this material, broke in half. And so you had two cores inside the star, both of which were accreting material, and then the star detonated. You were left with these two neutron stars. And then the neutron stars spun like almost instantly into each other again, and you got the kilonova. And so you got a kilonova and a supernova, supernova to kilonova, like roughly at the same time. And this is thought to be the first time this has ever been seen. Now, it could be that there are others out there, and so maybe this is a very common event, that stars during this supernova process can actually tear their neutron stars apart, which then get collided again. We've got a story about this from Scott Johnson. Every week we do a vote on our channel where you tell us what you thought was the tastiest space bite. And the tasty treat last week was a new method for measuring the Hubble constant. So thank you everybody who voted last week. We're going to put the vote for this week's episode into the post tab on YouTube. So if you want, you can go there, vote, or just subscribe to the channel, click on the notifications bell, train the algorithm that you like to vote on our polls. Do you remember the movie They Live? This is where Rowdy Roddy Piper has a special pair of sunglasses that show him aliens. And when he puts the sunglasses on, he sees regular people, and then he can pick out the aliens among them. And he takes the glasses off and they look totally normal. Well, there is a version of this in astronomy that has recently happened where regular telescopes just see normal galaxies with normal star formation rates. And then James Webb sees the raging monsters that are out there. So it happened with this classification of galaxies. We've been talking a lot about these little red dots. And so one of these is named Virgil, and it's seen about 800 million years after the Big Bang. And we know of now hundreds of these little red dot objects. They're very similar, very compact objects, seem to have a lot of dust in them. They're very red compared to other galaxies, seem to have star formation, active supermassive black holes at their hearts. And so when you look at this object Virgil in regular telescopes, you see normal amounts of star formation, seems to be a fairly regular galaxy at the time. But when you see it in James Webb, then it is much brighter, huge amounts of dust and heat is being generated at the center of this galaxy, that there is a supermassive black hole that is both obscured by dust and is also feeding at a rapid rate. So astronomers are calling this a Jekyll and Hyde galaxy, but I think it's a They Live galaxy. And so once again, we've got just this great application of this special infrared view that Webb gives us, where it's able to look through the gas, the dust, able to perceive objects in these different wavelengths that show them behaving in different ways, and shows like you kind of need to see the entire electromagnetic spectrum whenever you're looking at various objects out there. I've got a story about this from Evan Goff. And here is your bonus story. Now, Webb has been used to try to find atmospheres around exoplanets. And we've seen atmospheres around non-Earth-like worlds. So giant planets, hot Jupiters, things that you would not classify. You would not want to live there. But the dream, of course, is to find and study an atmosphere around an Earth-sized world that is orbiting around any kind of star. Like, let's just start with there. And so, the classic example of this is the TRAPPIST-1 system, where you've got 7 Earth-sized worlds orbiting around a red dwarf star. Several of them are in the habitable zone. These would be ideal to examine with Webb. Hopefully we could tease out the presence of an atmosphere. And this has been tricky, really hard to do. And so now what was thought to be, okay, this will be our best example. We'll find atmospheres. That'll give us a sense. Now, while astronomers continue to struggle to figure out if there are atmospheres around the TRAPPIST-1 system, they're looking for other candidates. And there are some other candidates, Earth-sized worlds orbiting around red dwarf stars, and some have already been observed and no atmosphere has been detected. So they need a pipeline to be able to find these. And so astronomers recently went through a lot of the TESS data, which is NASA's satellite that is finding exoplanets, and they identified 5 potential candidate planets that are orbiting around red dwarf stars. Now, 3 of these are probably not going to pan out. They are too close, too much energy. They are too small, so they're not going to be able to hold on to their atmosphere with the amount of radiation that they're receiving and the killer solar flares coming off of the star. 1 is very close, very hot, but it looks like it is so big that it probably has the gravity to hold on to its atmosphere. And then another one looks like it's large enough. It's a little farther away from its star, has about an 11-day orbit around it. And so again, could be a good candidate world to be able to hold on to its atmosphere. Now, these have just been identified as candidates. Then hopefully someone will write a paper requesting time on Webb to do actual observations of these worlds. And it's a funny time right now. Like, we are before the day when we could say that there are other Earth-sized worlds orbiting around red dwarf stars that have atmospheres. We don't know the answer to this question. Obviously, Earth has an atmosphere, so we know that an Earth-sized world orbiting around a sun-like star can hold an atmosphere. We know Venus has an atmosphere. We know Mars has an atmosphere. So sun-like stars probably are going to work. But red dwarf stars, we don't know. And the problem is the red dwarf stars are the ones that we can observe with the current tools that we have available. It's going to take a next generation of telescope before we can actually make those observations. And we need practice. We need to be able to develop the tools, the techniques, to be able to do observations as a planet is passing in front of its star, detect the presence of the atmosphere, figure out what its constituent elements are. And so far, this has turned out to be a lot harder than what everybody was expecting. Got a story about this from Andy Thomaswick. And if you want even more space news, we are working on dozens more stories over on Universe Today. We can only really get to a fraction of them here on Space Bites. And so you can go to the website, bookmark the Universe Today website, then return to that bookmark to see what new stories we have, or subscribe to us on your RSS reader so that you will get new episodes as soon as we post them without you having to get some social media algorithm telling you what you can and can't watch. Or subscribe to our weekly newsletter. Now, I write this thing entirely by myself, contains links to every single story that we're working on, all of the videos, all the podcasts that we've released, all in one place. There's no ads. It's completely free. Go to universetoday.com/newsletter to sign up. I'm going to talk about us wrapping up 2025, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Cy Nelson, Darkfinger, David Gilton, David Matz, Evan Pro, Greg Feely, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Sitz, Michael Purcell, Nordspace, OneStepForAnimals.org, Paul Rohrbach, Ren Kaibu, Richard Williams, Sean Sargent, Stephen Fowler Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldaborg Galactic Defender, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So we did it. We made it to the end of 2025, and we did not miss a week of Space Bites. So despite me being in Thailand, we released Space Bites. So a huge shout out to Anton Poznikov, who is, of course, the editor and producer for these videos. He is strict and maintains a rigorous schedule despite my flailing around. And so I think I have to really give a huge thank you and a congratulations to Anton for keeping the flame going all the way through 2025. He's got big plans for 2026. I've got a lot of interviews in the works. He's got a lot of ideas for other shows. And so hopefully we'll be rolling those out. I have no plans to do anything in 2026 so far, go anywhere, see anything. I'm sure I will eventually. But for now, we're going to be focusing just on content, making Universe Today the best space reporting news outlet that exists in all of existence. And thanks to all of your support last year, which was really a game-changing year for us, I'm really looking forward to what happens in 2026. All right, I hope you had a great holiday, and we'll see you all in the new year.